This is session 12 for models in epidemiology and biostatistics. I'm Gordon Hilton Fick. Well, in the last session, we looked at our first exploration of outcomes that are not dichotomous. Well, now I'd like to take some time and explore a second type. So the first type we had was when the outcome was essentially either nominal or ordinal. Perhaps the next step into the world of outcomes is when we have counts. And we'll see that this brings us to issues of incidence rates, and further, we'll see that there's a wide range of models available for the investigator to consider when the outcome is a count. Now, we should go back and point out that, in fact, some literature, some authors would argue that in some instances, even though the outcome is a count, that we might consider grouping. For example, it might be that the real issue is whether or not the count is non-zero or not. For example, we might be interested in counting the number of teeth with cavities in young children. And in doing so, the real issue might be just whether or not the child has any cavities at all. So if we were to dichotomize, is this sometimes the phrase, then we would be going back to a dichotomous outcome. Now you could say, wait a minute, you've just ignored a whole range of possibly important information regarding the actual number of non-zero counts, right? So that also suggests that perhaps we might take that count data and construct further groups. Then we're in the world of ordinal outcomes. So, for example, we were to decide on, stratifying or, grouping the count outcome as, say, 0, and then 1 to 3, and then 4 and more. Then we have 3 levels. Okay? So that's kind of in play here. Now, there are many authors that would argue that grouping might not be what's driving things, and what we're more interested in is the actual counts. We are interested in things like counting the number of days in hospital, or the number of days in an ICU, or the number of visits to a clinic, say for pregnancy, keeping track of a whole range of different outcomes that are counts and where the actual count is important. But now you can see that in principle there would be far too many values of those count outcomes to build a model that addresses each possible count. I guess in principle, with a large enough data set, one could contemplate that. But now we're coming to our first illustration in which the distribution of the counts will be important in understanding how we carry out an assessment of the relationship between a count outcome and explanatory variables. And if I may, perhaps one of the most well-known studies goes back to the 1960s, an attempt to understand deaths due to coronary heart disease and smoking status, a very early exploration of this type. And the way in which this data was presented was to stratify on age. So we've got, as you can see, the number of participants who died, and then here we have their exposure, if I may. These numbers, so-called person years, That's where we count up for each person the number of years of exposure. Now, that is more of an epidemiologic issue, and I don't propose that we discuss that any further here, except that such an approach based on person years has a lot of currency and has a lot of merit. We can also see that now we're dealing with quite large counts here, for example, among the smokers. And so we're not in a position to talk about, per se, the actual number, the actual count, but rather we're interested in characteristics. Again, very, very, very classic epidemiology. In other words, now we're interested in the construction of incidence rates. And again, there's a large literature on incidence rates and their estimation. Here it's quite straightforward. If we wanted to construct an estimate of the incidence rate for the smokers in the youngest age group, we would take 32 and divide by 52,407, right? That is an estimate of an incidence rate. Then we might take that particular estimate for the smokers and divide it by the estimate for the non-smokers, which would be 2 divided by 18,790. And then that means we get an estimate of an incidence rate ratio. And the symbolism that's widely used is IRR. And you can see that, in principle at least, the construction of the estimates is not complicated. It turns out that methods for constructing confidence limits for these incidence rates and these incidence rate ratios is also well established in the literature. In fact, exact methods are available in settings like this based on the binomial distribution. Pretty straightforward stuff. And in fact, if you're interested in maybe a bit more about the methodology here and the methods and the formulas that are used, I would refer you, for example, to the Stata help files. And if you go to the section on methods and formulae, you'll be able to read more about just exactly how these confidence limits are created and a whole lot more. So we'll for example, if we were to input the data and list that data in Stata, you can see that we've got the 5 age categories with codes 1 through 5. Smoking status, here the smokers coded 1, the non-smokers coded 0. So here we're looking at exposure, right? Exposure is the smoking variable. The age group is viewed as a potential confounder modifier. And then we have the raw numbers here. Well, it turns out that a part of Stata's Epitab module is a command called IR for incidence rate. And we can get a stratified analysis now for the incidence rate ratios. And so here we have the 5 estimates of the incidence rate ratio, one for each age category. So just to remind you again, this number 5.73 would be, in fact, 32 over the 52,000, all divided by the 2 over the 18,000. And that gives us the estimate of this first incidence rate ratio, and you can see that it is the largest. So that in the group that was coded 1, which was in fact the youngest individuals, we got what you might argue is at least visually, quantitatively from these numbers, the strongest association between smoking status and incidence rate. And you would see straight off the bat here, we get exactly the same principles that we've been using with dichotomous outcomes and with ordinal and nominal outcomes. We get in this case, the stratum-specific estimates of the incidence rate ratios. We get a crude estimate and we get an adjusted estimate. But we can see here that this particular process details something that gives us a test of significance, an omnibus test, that being the 5-1 differences among these 5 incidence rate ratio estimates. And we get a p-value that is interesting. And so then we would argue that then there appears to be evidence of a difference between the incidence rates by age, right? So that age appears to modify the incidence rate ratio. So we could argue then that the study of crude and combined here is irrelevant. Even though the software gives it to us, we would argue that these age-specific incidence rate ratios are the important part to this. Okay? All right. Notice over here, Stata points out that the confidence limits available for the construction of confidence intervals for the incidence rate ratios are exact. And here, again, I can refer you to the methods and models and formula, but it's essentially based on the binomial distribution. Not that hard, actually. Okay, so what do we get? We get evidence of modification, yes, which is, again, my point here is that although the outcome's different, we're getting the same epidemiologic issues, the study of modification, okay, and or confounding if we were to be directed there. All right, now let's take some time and think about how one might model what we just saw. So what we have is the population characteristics now, rather than the observed count or the observed number of deaths. We then are interested in studying the expected number of that count, okay? Here are the number of deaths. So now we are in the world of a characteristic that is coming from a probability distribution for the number of deaths here. Further, we're interested in the population now incidence rate, which is the ratio of the expected number of deaths to the person years. And now we're going to see something that is familiar again, the mighty logarithm. Yay! It turns out that if we take the logarithm of this ratio, well, what do we get? The difference between the logarithms. Yep. And if we then imagine that such a difference will be modeled in terms of a set of explanatory variables like this, then we see that in fact we're taking the outcome here, the actual variable part of things, that is the number of deaths. This is the thing that has a probability distribution, and expressing it as the log of the person years or the log of an exposure characteristic more generally, and then the sum of the weighted sum of the regression coefficients times the explanatory variables. So now we're in familiar territory, almost. There's a part to this that's a little new, a little bit different, and that is the notion of the offset. The idea being that we are adding this term to the right-hand side of the equation, the offset, and it's worth noting here that there is no regression coefficient in front of it, okay? There's no beta there, okay? That's what's in play. And Stata is set up in such a way, as is all of the standard software, when one is modeling counts, to enable this offset. offsets are seen and come into usage in a wide range of settings, and this is our first usage of the notion of an offset here. You don't have to take the logarithm, by the way. Stata does that for you. Okay. So we're working with now a variable, which is the number of deaths. And we are interested in a characteristic, the logarithm of the expected number of deaths. What about then the distribution for the number of deaths? Okay, here we can think of now probability distributions. The most classic, the oldest perhaps, and still often widely used distribution for the number of deaths here, or the count, is the Poisson distribution. And perhaps you saw this in your previous study in perhaps maybe even a course on probability or probability and statistics. This distribution involves some intimidating looking things, an exponent, a factorial, yes. However, the real key is that's important here, I guess, is that the expectation is given by this quantity, usually written with the Greek letter lambda. And there's a relationship between the binomial distribution and the Poisson distribution. So it turns out that if we have a very small probability and a large number of trials, that we get a distribution that begins to approximate better and better the Poisson distribution. That's one way in which one often sees the Poisson distribution for the first time. And here's a little bit of the details. Maybe more crucially for us here, though, and for the analyst, is the fact that, well, once one knows the mean of this Poisson distribution, we have essentially determined that distribution. So the study of the mean of a Poisson distribution means if we knew the mean, then we know the distribution, okay? There's a one-to-one correspondence here. And maybe another issue that's not quite so obvious, and again, a little bit of technical matter here, but it turns out that the variance of the Poisson distribution is in fact just the mean. So the distribution, Poisson distributions are characterized by their mean, and the variance is the same as the mean. Okay? And as we'll see in the application of the Poisson distribution in the analysis of count outcomes, this issue of this variance being the same as the mean becomes an issue. And we'll be exploring that. Okay. So what I'm going to do for illustration here is show you how you might carry out an analysis of the Dahl-Hill dataset. Again, the model-based equivalent to the classic stratified analysis we just saw. And so now we're going to be getting the, and by the way, I've reverse coded age groups so that the age group coded one here is now the oldest group. And so that we will then be looking at essentially differences between a particular age group and the oldest group, rather than as it was given initially, where we were looking at differences, or we could look at differences relative to the youngest age group. Again, what I'm attempting to do is spin this for you in terms of what is the group that has the biggest challenge, and it turns out here it looks like it's the youngest, right? We saw that. So what do we get? Well, we get logarithms of incidence rate ratios. We get the estimates of the logarithms of the incidence rate ratios. Okay. So, for example, if in fact we were to write out, and I would encourage you to do so, to write out this particular model in terms of the regression coefficients and the offset here, coded in stata very nicely by person years, we get an exact duplicate of the estimates we saw in the stratified analysis. So, for example, if we take the exponents of the regression coefficients, then we get estimates of the incidence rate ratios and ratios of incidence rate ratios here. So, for example, the estimate of the incidence rate ratio in the oldest age group is 0.904. And if you go back to the stratified analysis here, you can see that you get exactly this number, 0.9047, okay, for the oldest age group, because I reverse coded the age group. Okay. And then we get, just as nicely here, we get that this number, for example here, 6.34, is the estimate of the ratio of incidence rate ratios, that is, the youngest age group relative to the oldest age group. And in fact, that estimate of the ratio of incidence rate ratios, number 6.34, we can see reproduces the incidence rate ratio for the youngest age group by merely taking the estimate in the oldest age group and multiplying it by the estimate of the ratio of the incidence rate ratios. A little bit technical here, perhaps. Further, we have a methodology that is based on the likelihood function, just like we had in logistic regression. Okay. So the quantities that we're getting here may be slightly different from the quantities we would get from a stratified analysis, where the methodology for constructing the estimates of the standard errors and the confidence limits are slightly different. Further, we can see here that we get, rather than the omnibus test based on 4 degrees of freedom for differences among the incidence rate ratios, the age-specific incidence rate ratios, here we get specific comparison, the tests, the walled tests for specific comparisons. For example, that this particular p-value is associated with a test of whether or not the incidence rate ratio for the youngest group is different from the incidence rate ratio in the oldest group. And we get quite a low p-value, and it's interesting here that we also get evidence of a difference when we look at the second oldest group compared with the youngest. We also get something interesting. So notice that this Poisson model, Poisson regression, is giving us a way to separate out the degrees of freedom of the omnibus test we saw. Now, you could do the same thing as we did with logistic regression, and you could think of a model that does not include these product terms and compare it with the model that does include them, and that would be a likelihood ratio test, and that likelihood ratio test would be a direct analog to the test for homogeneity of incidence rate ratios. So we can see that the techniques we've developed for modeling in all the earlier sessions can be applied here, and that you have the option, for example, of interpreting the logarithms of the incidence rate ratios directly, that is the regression coefficients, or taking the exponents and getting incidence rate ratio estimates directly, or, as we saw, possibly ratios of incidence rate ratios, or more elaborate things if, for example, we were to have an explanatory variable that's measured. Then we would have things like rate of change of the logarithm of the incidence rate ratio per unit change in something. So we have that all in our toolkit, just like before. And as I mentioned, the likelihood ratio test for the Poisson model is available just like before. Just like with logistic regression or with the proportional odds model or any of the generalizations. So we've built the framework for understanding the key ingredients and what's happened. Well, instead of discussing the logarithm of an odds, here we're studying the logarithm of an incidence rate ratio. So in a way, all we've done is we've changed the left-hand side and we've added the possibility of having an offset. But that the methodology, the way in which we go about studying these things does not change. Now, next up is the fact that, as I alluded to earlier, there are certain instances in which the distribution for the counts will not be Poisson. And this has been an issue that health researchers have explored and dealt with for some time. It turns out that in certain instances, the Poisson distribution is not a good choice. And oftentimes that is because of the fact that the Poisson distribution is determined by its expected value, right? And that we would like to have a more flexible set of distributions that enable us to study characteristics beyond just the expected value of the distribution of those counts. The most widely seen is usually called the negative binomial distribution, or it is in some literature called the Polya distribution. So that's what we're going to explore next. Okay, the next little bit is slightly bit more technical than what is the norm for these sessions, but I think you'll find it to be of some merit. Or you can fast forward through it. So it turns out the negative binomial distribution can be established through a property, that is, the distribution of the number of failures needed to achieve our successes. So that basically, that particular issue or that property, in fact, shows us the connection with the binomial distribution, even though these distributions are very different. The negative binomial distribution, like the Poisson distribution, does not per se have a largest value. These distributions, in principle, take on all possible counts, right? There is no upper limit. Now, in practice, of course, there would be some practical limit where the probabilities for a large enough number of counts is a tiny number. But more crucially for us now, we can see that the mean and the variance of this negative binomial distribution are not the same. Okay? So the variance typically can be larger than the mean. That is the most often seen. Then we come to a new notion, perhaps, for many of you, and that is the notion of a dispersion. The dispersion isn't that fancy. It is merely the ratio of the variance to the expected value. So for the Poisson distribution, the dispersion is always 1. And it turns out for the negative binomial distribution, the dispersion is always greater than 1. And it is precisely this dispersion issue that many investigators want to understand, that they'd like to be able to assess the dispersion and whether or not, in particular, the dispersion is meaningfully larger than 1. So there's various ways in the literature for establishing an assessment of dispersion. One way is the so-called constant dispersion model. A little bit technical here, but where we have now the study of the expected value in terms of regression coefficients, and then we study a quantity called delta here, where 1 plus delta is the dispersion. So you can see that delta is a quantity that is greater than or equal to 0 for the negative binomial distribution. And then there's ways of expressing the mean and the variance in terms of the dispersion. So here you can see that we get the relationship between the characteristics from the negative binomial distribution and its mean and its dispersion. So a little bit technical here, but nevertheless, you can see that a test for here, the word is over dispersion, or a dispersion that's greater than 1, is enabled by testing whether delta is greater than 0. Remember, 1 plus delta is the dispersion, and so delta being greater than 0 is an indication of evidence against the Poisson distribution here, right? Evidence for a negative binomial distribution. There's another way in which one sometimes sees this particular quantification of dispersion done. Stata does multiple versions of this. These are I'm showing you first here, the first two most widely seen. The constant dispersion approach and the mean dispersion approach. And here, the difference is, you would say, somewhat slight. We have the expected value in terms of explanatory variables as usual, and then a quantity alpha, where alpha is, in fact, related to the mean. So we're capturing how the mean impacts on the study of the dispersion. So alpha then, again, if alpha is 0, you can see there is no if alpha is 0, then we would say the dispersion is 1, and we're back to the Poisson. On the other hand, we can see here that this relationship between the mean and this quantity alpha are related to the characteristics for the negative binomial distribution, which are displayed a bit earlier here. In any case, we can see here again that testing that alpha is greater than 0 here is a test for overdispersion, or evidence against the Poisson distribution being used to model counts. Well, it turns out that it gets wilder. We can also have that the dispersion itself can be modeled in terms of explanatory variables. The most widely seen is when one models the logarithm of this quantity alpha in terms of its own set of explanatory variables. So we model the mean in terms of explanatory variables and model the quantity that is capturing the nature of the dispersion in terms of explanatory variables. Widely seen in this literature. Okay. Now we come to, you would say, wow, time for an example, another example. And this one I am borrowing from the Stata website and a project that was first published by Rodriguez. And I can refer you to that particular page for more of the details. So this is what the data set looks like in this instance. So now we've got a collection of cohorts, which are viewed as the exposure. So we have cohort 1, cohort 2, and cohort 3, which are the exposures. We have, in addition, an explanatory variable, an explanatory variable age here. And you can see that there are some there is some grouping, and in each of these groups we have collected together the indication for that particular age group is given by the median in that particular age group, and that's done so for each of the different cohorts. And then again, we have, as before, we have a measure, we have a count, and here we have a quite large numbers, and then a measure of exposure. Like in the previous article, exposure was captured by person years. Again, I'll refer you to the article for more of the details here. Okay. And here is, just for illustration, what an analysis, for example, using Stata would look like here. This is not intended to be in any way a definitive analysis, only just to illustrate how one would use both the Poisson model and the negative binomial model in this particular data set from Rodriguez. As I mentioned, many authors, certainly before the advent of the use of the negative binomial, might begin an analysis using a Poisson model. And here's, for example, we'll think of the cohorts here. So here we have these are the exposure groups. And here the baseline group is cohort number 1. And then we have regression coefficients that give us differences between the characteristics for cohorts 2 and cohort 1 and cohort 3 and cohort 1. Okay. Now, in this instance, one might say, is this an acceptable analysis? Here I'm not showing you the analysis adjusted for age group, but you may find it of interest to explore this. In any case, what we can do, and what has been around for quite some time, is to construct a goodness of fit test for the assumption of the adequacy of this Poisson model. Or another way to put it is there evidence against the assumption that the variance is the same as the mean? Or evidence against the Poisson form of the distribution of deaths. And what we get here is very low p-values in this case, showing us that we're in trouble here, that the assumption of the Poisson form for the number of deaths, Poisson distribution for the number of deaths, is discredited here. Now, the real issue is are there meaningful differences between these numbers and an analysis that correctly handles the distribution or attempts to correctly identify the correct distribution for the number of deaths? And so that was the big step forward, frankly, in the literature of Poisson outcomes, and of count outcomes, and that is the fitting of these negative binomial models. And that can be done very easily using the NB rig here. And if we do so, we have a fitting display here that I won't comment on here. It's a topic for later, but the challenge of, has the software adequately determined the maximum likelihood? and is all well. I'll leave that for now, but you see this all the time, just as we did with logistic regression and with proportional odds and so on, that we get an iteration log. Leaving that aside for the moment, the real issue for us is that we get an indication, we get a likelihood ratio test here using the mean dispersion model here. We get a likelihood ratio test for alpha equals 0. Now, there are some technical issues here. This particular likelihood ratio test uses a distribution we've not seen before called the chi-bar squared distribution. And again, I would refer you to what is a quite extensive literature on chi-bar squared. It turns out it's an interesting distribution, that it's a combination that has a distribution that has a continuous part and a discrete part. But for us here, the issue is we're getting, like we saw from the likelihood ratio test, goodness of fit test, we get strong evidence against alpha equals 0. You'll recall that alpha being greater than 0 is providing us with evidence of overdispersion. Right. And so the actual estimation process is done on the logarithmic scale here. You can see this is the logarithm of alpha, and then the exponent of it giving us the estimate of alpha, which you can see is not 0. It's not near 0. And the confidence limits for alpha here, definitely not close to 0 here. Okay, this distribution, though, is testing a null hypothesis that is said to be on the boundary of the parameter space. That's part of the reason why this is a little bit tougher. These boundary issues that plague a whole range of things in biostatistics. Okay, but you might then, frankly, really want to give your attention to have the regression coefficients that are enabling us to explore the differences between the cohorts and their impact on the incidence rate ratio. Okay, because remember again, these are differences between the logarithms of incidence rate ratios, and you can see here that the numbers we get here are, let's go back to the Poisson, are not the same. Here are the numbers we got from the Poisson model, which suggested there is an association if I were to look at the second cohort compared with the first. We appear to have evidence of a difference between exposure level 1 and exposure level 2 here. However, when we analyze this with the negative binomial approach, we do not see that difference. So it could be then that this difference between the logarithms of the incidence rate ratios that we saw with the Poisson approach might be an artifact of the fact that the model was incorrect. Okay, well, just a little bit of the challenges one can face with this type of project. So this was with mean dispersion, and now for illustration, we could repeat this process with the constant dispersion model, and there's not much happening that's materially different. Notice now we're looking at delta. Delta is definitely not equal to 0 here. It's a huge number. Have strong evidence of overdispersion. And again, the messaging about whether or not cohort 2 and cohort 1 are capturing the same impact on the logarithm of the incidence rate ratio is interesting, isn't it? All right, just for interest's sake, again, we could repeat all of this with an even more elaborate situation in which we, just for illustration only here, we could have, for example, that the incidence rate ratios are modeled in terms of the age groups, at the overdispersion measured in terms of exposure. I'm not necessarily suggesting this is the way one would want to do it, but it's one way to look at this. This is the so-called generalized negative binomial regression. Right. And here you can see we get now more things to discuss. We get whether or not the death rate, incidence rate ratio is a function of the age, and sure enough it is, right? Okay. We'll leave that for you for your study, and I won't give away any surprises here. You can you can take a look at this data and see what you think. Okay. And there's means of making individual comparisons. For example, suppose instead of wanting to compare cohort 2 with cohort 1, one wished to compare cohort 2 with cohort 3. There's a test process that one can use here. Lots going on here. Again, all of the tools we've developed in the first 11 sessions are all applicable now. It's just that we're changing how we describe the regression coefficients and their estimates because the left-hand side of the regression equation has changed. I wanted to single out a very wide range of further examples of the use of software to carry out analyses like we've been doing so far in these sessions that were put together by the folks at UCLA, University of California at Los Angeles. And you'll see here that they have provided you with a whole range of different topics, and some of them we've already discussed in this course. We've discussed, for example, logistic regression. We've got the proportional odds model, the multinomial model. We've got Poisson models, negative binomial models, and some other things we're going to discuss next. So the point being here is that, or I guess my comment for you here is that if you were to want to see more illustrations of the use of, for example, Poisson regression or negative binomial regression, you get another nice example, for example, using Stata. Or, for example, there's also comparable illustrations with the same projects, with the same data sets, showing you the analyses in R. And in fact, as I mentioned earlier in these sessions, there's a fair bit of argument now about what we should be using for introducing models in epidemiology and biostatistics, and what software would be the right one. And there's lots of discussion about that. Oh yes. Oh well, that's all for now on this. So as I mentioned, there's quite a bit of literature on how investigations can be done of count outcomes. Certainly the use of the Poisson and the negative binomial models are widely seen. But now gaining a lot of attention are two types of extensions that must be given some consideration in a wide range of settings. And that is that sometimes the zero count is just different. That there's issues connected with having no count, having a count of zero as an outcome, as being different from the non-zero counts. There are two issues that are seen. One is so-called inflation, and the other is truncation. With inflation, the most sound way of perceiving in inflation is when the zero counts are affected by something other than the distribution that's in play here. So we might have that the distribution of counts is adequately handled by, say, a Poisson distribution or negative binomial distribution, but not for the zero counts, and that the zero counts need to be handled differently. In other words, there might be, and sometimes the language that's used here is interesting, the so-called regimes. We can have regimes that contribute only to the zero, and a regime that handles the zeros and the non-zeros. Okay, and so that's what we'll be looking at next. Just as sometimes we can have too many zeros, in other words, the Poisson and or negative binomial distribution does not give us enough zeros, there are another set of instances in which zero is not even possible. So the data are very definitely counts, but zero is not possible. For example, we might have a study of the number of days that a person spends in an ICU, and 0 days is not measured, right? You're only counting non-zero days. That is, the decision to admit someone to an ICU then means they are contributing to their first day. Now, there are other instances. One could say that there's two issues again. That why is it that, say, a person admitted to hospital is then under consideration for admission into the ICU? And here is where a zero and a non-zero are both possible again. But again, there's very different issues sometimes in play here. Okay, with zero inflation, we have two types of models. We have the zero with the ZI for zero inflation Poisson, and ZINB for zero inflation negative binomial. Now, on this slide, which I have regrettably not updated it for the last few years, I'm mentioning this test for zero inflation. The literature on this has changed quite a bit in recent years, and investigators have pointed out that this test for zero inflation is not appropriate. So this mention of this particular test I should not have included here. But if you see it used in a particular investigation, my suggestion to you, it would be to explore this literature connected with this particular test. And there's quite a bit. If you simply do a search on this particular test, you'll get a number of articles that point out that zero inflation should not be assessed with this particular test, this Vuong test. Okay. So there's issues where a zero inflation can be seen. And sometimes there are plausible regimes, that is, the regime for the zeros and the regimes for the non-zeros, that can be formulated. Sometimes the data itself will give you an indication that the zero counts need to be taken into consideration, maybe because you see a display in which the zero counts are obviously larger than they should be if the distribution was, in fact, say, Poisson or negative binomial. Well, we'll take an example. This example is taken from the very fine book by Dohu et al. From the University of Prince Edward Island, actually, and a highly recommended textbook of a wide range of interesting epidemiologic issues, and well written and well presented. Here then, very briefly, is an indication of what the analysis would look like, for example, using Stata, where we're interested in a zero inflation issue. on a slide that can be shown here, and I'll show you it after I show you the output. But one can use something, for example, like a spike plot to look at this particular outcome in this particular project and see that there's just too many zeros. And so we can, using this particular implementation of the zero inflation negative binomial model, consider a range of explanatory variables, okay? And we can consider variables that might impact on the zero inflation. And as before, we can have an exposure characteristic, just like more generally. Again, if you want to see more of the explanation here, I would refer you to the book by Dohu et al. In any case, this is what the output looks like. It's data. We get the regression coefficient estimates as usual, but then we, in addition, get regression coefficient estimates for the zero inflation. And you can see that there's issues here that may be helpful in understanding why there's zero inflation. So the zero inflation negative binomial approach gives us, for example, with the approach using a mean dispersion with the negative binomial, an estimate of the logarithm of alpha, and an estimate of alpha itself, which is the exponent. And this is giving us an indication of the overdispersion. And then we have, in addition, we have the indications here, which you can explore and study for the indication of zero inflation. So as promised, this is the visual of the distribution of the outcome here. And you can see that we've got a curious display that is perhaps fine, except for this bump at zero here. You might think that's not much of a bump, but on the other hand, we would anticipate declines here, and that zero should be perhaps less. And in fact, they're higher than you can see this value. I guess this is for 2 here. In any case, the point being here is that we do get some indication of zero inflation here, and the model gives us some indications of why we might have been seeing such zeros in this particular project. Okay, and then I'm showing you the results again. Incorrectly, by the way, with this output, including this test for zero inflation. So please disregard this. More recent versions of Stata will give you a warning if you try to use this. Okay, enough. So, to my knowledge at least, there are no appropriate tests for zero inflation at the present time. But that, again, you may want to do a lit review on that and see if, in fact, this literature has improved or has changed since I last had a look. Okay. I should also mention that a colleague of mine, Dr. Lindsay McLaren, has contributed to a study showing the relationship between cavities in children and fluoridation, a very complicated issue. And this study of Lindsay's back in 2016. And my point for including it here is that this is an instance in which Dr. McLaren used a zero inflation model in order to assess this particular outcome, that is the number of cavities. And there really was a distribution of cavities, of cavities in these children, but that the group of children that had no cavities was different from those. So there was an indication of a regime that came up. So as I mentioned, there is indeed an interesting literature on truncation, the circumstances in which a zero count is just not possible, or it is argued that the zeros are excluded, and there are sound reasons for doing so. So, continuing on with this, there's two ways in which one can explore the truncation issue. The oldest and the simplest is to simply recode the counts. In other words, if 0 is not possible and they start with 1, then take the count and subtract 1, and then use an analysis based on the Poisson or the negative binomial. And then put the 1 back when you go to construct the confidence limits. Okay? So you might think that that might well be a perfectly sensible approach. However, there is a way of handling the truncation either with the Poisson or with the negative binomial. This is zero truncation. That does not involve this subtraction of 1 from the count, and analyzes the distribution of and the assessment of truncation on its own as an issue. In other words, the rationale for truncation. And so that's in play. So here is a very brief introduction to the analysis of truncation, where we have the length of stay recorded. Okay? And we have an interest then in modeling this length of stay. And we wish to do so, for example, by subtracting 1 from the numbers. You can see there are no zeros. So the idea would be, all right, subtract 1 and then analyze that difference between the length of stay in days and 1. And do so, for example, with a negative binomial model. And then we might think that, okay, this length of stay modeled in terms of the age, in actual measured age of the participant, a characteristic related to this is an American designation of their health coverage, and then another measure of whether or not they died. There's quite a bit involved with this project as well. In any case, the point being that we get a set of regression coefficients, and as usual, a test for overdispersion, and well, we're definitely getting an indication of that here. And this is with the zero truncation removed by subtracting 1 from the counts. And then directly modeling the truncation. A zero truncation negative binomial model can be done, and the implications are not very different. Okay? I'll let you have a look. In fact, it is worth noting that these two approaches are not the same. And again, you may wish to explore the implications in advance, and perhaps your literature review might guide the decision as to which approach to use. I would say that probably the model-based approach, this zero truncation negative binomial approach, might be the one that is deserving of more attention. For example, if we were to look at these regression coefficients here, we get an interesting set of indications of circumstances in which we get apparently statistical significance, and we get very much the same information from this arguably simpler approach here. Anyhow, that then concludes our tour through a arguably very brief introduction to the analysis of count outcomes, and the quite wide range of issues that you might face.